Today we're going to look at this is the Hubble Deep Field North. So so an introduction. In 1996, astronomers had NASA. Now NASA had launched the Hubble Space Telescope, and here's a picture of the Hubble Space Telescope. And they were pointing it at what appeared to be an empty spot in the sky, where astronomers hadn't seen any stars before. Now it was a little bit of a risk because they could have looked in there and not seen anything. So where they were looking was an area near the Big Dipper. So as you see here, that little red spot is where they pointed the Hubble Deep Field. Now, the actual image, if you held a piece of a grain of sand, arm's length, that's about the size of the sky that the Hubble Deep Field is looking at. Okay, and so they pointed there for 10 days. Now the reason, basically the Hubble can do this is, well, it orbits around, and then whenever it has a view of the sky, it looks at it, and then it collects the light. So the light kind of comes in and enters into the light collection area, and so it does that day after day after day. So it can pick up very, very faint photons of light, which is what they did. And then afterwards, they looked at the image, and this is and then after the image was collected, the Keck telescope, which is on Earth in Hawaii, was used to observe some of the faint blue galaxies in the image. And they're estimated, the blue galaxies are estimated to be the most distant objects ever seen. So can you guys see some of the blue objects that we're talking about? And as you can see, there's one up in here. There's another one right here. And then there's another one right here. Okay, and there's another one down here. And so those are the blue images, which represent the most distant objects that we can see from Earth in the universe. So the first step in your lab is going to be with redshifting. So the figure to the right, so this is the Hubble Space. You have noticed that you have the same image, but it's not, instead of in color, it's in black and white, and it shows the redshifts written next to them. Now, I have an equation down here. Don't worry, and I'll go through a sample equation, but don't worry, you're not going to have to do that equation and do a bunch of calculations. They've already been done for you. As you can see, each one of these has a number next to it, so those are the numbers that we're going to use. But I want to explain what those numbers mean. And the way they get that is you have the wavelength of the light. So each one of these is producing a wavelength of light, and you have a peak wavelength. And more specifically, they're looking for the hydrogen spectrum. Hydrogen, because it's the most abundant element, and it's what's going to be where you're going to get most of the nuclear fusion is going to occur hydrogen. And so they can see how much it's been shifted, and then compare that to what the rest spectrum is supposed to look like, and then that is going to give them a Z value, which is a redshift. And let me show you guys more what I'm talking about. So if we look here at this illustration, the top one is our rest frame, okay? And so this is a spectrum of hydrogen, and you can see you have the peak at this point right here, okay? And that peak is going to be associated with about 6,500 angstroms, or 650 nanometers. Maybe a little bit more, but around 6,500 angstroms. And let's look at the next one down. So we have the next one down, you see the peak is changed. It's moved. It's no longer at 650, it's now at about 7,800 angstroms. And so that creates a difference in wavelength. So where this wavelength was originated at here, it is now observed here by astronomers. And so we have 6,500 at rest, 7,800 as being redshifted. We plug those, we're going to plug those numbers into our equation, and we get something that looks like this. So The difference between 7800 and 6500 is 1300. We divide that by 6500, and we get a z value of 0.2. So what does 0.2 mean? So if you look here, these are the values that they gave. Now notice that my value that I calculated is not exactly what they have. They have 0.178. Now there's a reason for that. The reason is that astronomers they have equipment that is geared towards getting them the exact peak frequency. So where I rounded up and approximated my numbers, they would have more exact numbers. But notice how close the numbers are to each other. If we rounded this number up to the nearest decimal, to the nearest tenth, the nearest tenth of a decimal, we would get 0.2. So they're close. And if I had the exact numbers that the astronomers had, I would have gotten a number a lot closer to 0.1782. But I wanted to kind of demonstrate how this works. So the way the work of math, the higher the z value, the more the redshifted. So the more redshifted, the faster it's moving away from us. And like I said, don't worry, you're not going to have to do these calculations. I did a sample calculation so you guys get an idea of where these numbers are coming from, but the ultimate result is you look at the number and that's going to tell you how much it's been redshifted. All right, so what you guys are going to have for your lab is you're going to have this illustration that you guys see right here, and you're going to, I'll tell you in just a second, but as you see here, you have the different numbers, and small numbers are slow, large numbers are fast, and it also indicates how far away they are. So large numbers mean that they're further away, smaller numbers mean that they're a lot closer to us. And if we make a histogram of all of these, so we take a histogram of all of these and count, for example, if we count all of those that are about 0.2, and so where's one that's 0.2? I'm not really finding one that says 0.2, but that's okay because notice that there's not very many of them. But one of them that does have a very large number is 0.8. So let's see if we can, how many I can see that are 0.8, because that seems to be the largest number that is 0.8. Here's one that's close to 0.8 right here. Here's one a little bit bigger than 0.8, and they're kind of close together. There's one at 0.85, and so there's another one that's 0.78, which is also 0.8. So what they did was they went through and counted how many of them are there, how many of them there, and so on and so forth. They broke it up, and there's different methods of doing that so they don't double count and so on and so forth. So here's our histogram. And so this is, as you can see, these numbers right here were turned into a histogram, and this curve right here, what is that curve? Well, the curvy line represents an average of the data point, and it emphasizes the groupings of galaxies around certain redshifts. So you can see 1, 2, 3 groupings. So we got one grouping here, and a third grouping right here. So the first question for the lab is going to be, there are 3 redshifts for which galaxies seem to be grouped. List those redshifts. And I kind of pointed them out, but you need to tell me approximately what those numbers are and those values are. And that would be your first question for the lab. Next question, what redshifts do there seem to be few galaxies? And just look at the histogram, and you should be able to see where there's very few of them and where the dips are, and tell me where those dips are in that question to answer that question. Number 3, suppose that you had a bigger, more powerful telescope and looked even deeper into space. Speculate the number of galaxies you would expect to see the redshifts greater than 4. Well, 4.2, I'm sorry. The limit of this histogram, and so just kind of, it's more of an opinion question. So 4 is a very, 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 very large redshift. So does this represent the limit of what you can see, or do you think we could see a little bit further? And now the next part of this lab is going to be the three-dimensional distribution. So in the three-dimensional distribution, you're going to be using the redshift data that astronomers were able to construct a three-dimensional, and this is a three-dimensional image on the right. So as you can see, we're moving through it, and the closer or the smaller redshifted galaxies are moving faster, and they move off screen quicker. And whereas the further or the larger redshifted galaxies are going to move slower and stay on the screen longer. And so that's how they constructed this image right here, based on the redshifts, and it kind of gives a three-dimensional view of the deep field view. All right, so next question is to look for a group of galaxies that you would classify as a cluster on the grid. Look for a large group of galaxies with close to the same redshift value and circle it. You can do it either digitally or on paper. And so I gave an example. So I found these groupings right here that were between 0.4 to 0.47. And so that would be representing a grouping, and therefore they would be considered in the same group, about the same place in the universe, because they're about the same distance away from us, and they're and that's away, and then also in the X and Y, they're kind of close to the same area, so that would represent the same group. There are many more to pick from, and so you don't necessarily have to pick that one. So find where you have a grouping of stars that are, or a grouping of galaxies that have the same value. And then so then after you've decided where your grouping is, decide how much does the redshift among these galaxies. So in my example, it was between 0.4 and 0.47. So my answer for that one would be 0.047. The next question, suppose you noted clustering at redshifts of 0.2 and also 0.4. By how much does this velocity differ between the two galaxy clusters? Well, I'm only going to do one, and I'm going to let you guys do the other one. So the formula I'm going to be using is that the velocity is going to be equal to the speed of light times our redshift. So if we have a, the example I'm going to use is for redshift of 0.2, so we're going to take 300,000, we're going to multiply it by 0.2, and that gives us 60,000 kilometers per second. And then you guys, and all you guys have to do is do the same equation, but instead of putting in 0.2 here, you're going to put 0.4 and see what number comes up here. Okay, just simple as that, and that gives you an idea of the differences between the two values. Now, Hubble, back in the early 1900s, Hubble categorized many different galaxies that were that they could see with the telescopes. This was before they had the space telescopes, and it was all ground based, and they knew about how to do redshifting. And so what he did was he redshifted these galaxies, and what he found was that the galaxies were most of them were moving away from us, and the further away they were, the more redshifted they were. So this and this is where we get the idea that we have an expanding galaxy. So the next part is to calculate the distances of the clusters for the redshifts of 0.2 and 0.4. So again, I'll do 0.2 and you guys do 0.4. So the Hubble constant is 75 kilometers per second per mega parsec. That's mega meaning million parsecs. So that h goes in up here, and then the velocity is going to go in here. So this, so to figure out what the distance is, we take our velocity and we're going to divide it by the Hubble constant. So plugging in our values, we get 60,000 divided by 75, and when I calculate it, that got me 800 megaparsecs. So you guys do the same thing for the 0.4 a 0.4 redshift and see what number, how far away 0.4 redshift is from us. All right, so next question. Explain how the image of the deep field can give astronomers, and this is the last question that you'll have to do, can give astronomers insight on the evolution of galaxies. Astronomers examine the image of the galaxy in the Hubble Deep Field North because there are galaxies that show the universe at a relatively early age. Astronomers can compare these galaxies which are newly formed to near galaxies which are much older. This helps them understand the changes in galaxies over time.